Hello everyone, and welcome to Jam Academy. In this example, we want to calculate the stopping distance of a Tesla down a hill inclined at an angle of 15 degrees. Now, according to Consumer Reports, a Tesla Model X can actually brake to a complete stop at a speed of 70 miles per hour in just under 48 meters, or in just under 50 meters. Now the question is, what is its stopping distance on a road sloping downwards at an angle of 15 degrees? So we will analyze this. The very first step is we have to calculate the coefficient of static friction between the wheels of a Tesla and the road. And how do we do that? We have to begin by drawing our Freebody Diagram. You have the weight of our Tesla acts vertically downwards. The normal force is upwards. Remember that the static friction between the wheels of the tire, that the friction force between the tires of the car and the road is static friction. The reason is because the point of contact between the wheels and the road is actually at rest. So the only force that can exist is static friction. If it's kinetic friction, the car will just skid. And that occurs when you're driving on dry ice or on snow. The car can spin around or skid across the road. That explains at that particular moment, the static friction is kinetic. But on a normal dry road, the point at which the tires of the car is in contact with the road is relatively at rest, which means that the friction force acting on the car or on the tires of the car is static friction. So we have established the fact that the contact force that the road exerts on the tires of the car is static friction. But the most important question that remains is, in what direction is the static friction? Is the static friction acting forward? And under what conditions will the static friction act forward? Or is the static friction acting backwards? And under what conditions will the static friction act backwards? Now, the first point we need to remember is the car is decelerating, which means that the acceleration of the car is negative. Now, by Newton's third law, the net force acting on the car must also be negative. And if that force is negative, it means that the net force acting on the car is directed backwards. But think about it from a conceptual perspective. The car is decelerating. That means that the contact force that the earth exerts on the car is acting backwards, because that is the only force acting on the car from the earth. That means that for the car to decelerate, it must exert a forward contact force on earth, so that by Newton's third law, the earth will also exert a backward contact force on the wheels of the car. So we've established the fact that the static friction force acting on the car is directed backwards. So this is the static friction force exerted by the surface on the car. It's important you note that. This is only the case in which the car is decelerating. If the car was accelerating, the static friction force will be acting forward, not backwards. This is the weight. Which is the force that the earth exerts on the car. And you have the normal force that the surface exerts on the car. So these are the three forces that the car experiences. The next thing is that we need to write down the Newton's second law equations for the car in both directions. I often love to start with the y direction because the sum of forces in the y direction is 0. So we have NSC minus W. This is equal to 0. This means that the normal force that the surface exerts on the car is just equal to the weight of the car mg. Beautiful. Nice and easy. Now the next thing is the summation of forces along the x direction will be equal to, there is no force in the forward direction minus the static friction acting on the car backwards. This will be equal to m multiplied by a. Now, by definition, the static friction acting on the car is less than or equal to the coefficient of static friction multiplied by the normal force acting on the car. Now, this would mean that the static friction acting on the car is less than or equal to mu s mg. Now, as long as the car is rolling without skipping, the static friction force acting on the car is maximum. That is Fs max, which will be equal to mu s mg. So as long as the car is rolling without skidding, the static friction force acting on the car will be maximum. It's important you note that. So that means that that negative mu s mg will be equal to ma. The masses cancel and the acceleration of the car is negative mu s g. Clearly it's negative, which means that the car is decelerating. But our question is to calculate the coefficient of static friction. We are required to calculate the coefficient of static friction. So for us to do so, we will employ the kinematics equations of motion. We know that v squared is equal to v naught squared plus 2a delta x. The car decelerates to rest, which means that the final speed of the car is 0. So this would imply that 0 minus v naught equal to v naught squared minus 2 mu s g delta x. In other words, delta x is equal to v naught squared all divided by 2 mu s g. This expression will help us to calculate the stopping distance, but because we already know the stopping distance, we know the initial velocity, which is 70 miles per hour, and we know the stopping distance, which is about 160 feet, so we can gladly say that the coefficient of static friction, which is the unknown, will be equal to v naught squared over 2g delta x. So this is actually one of the ways in which the coefficient of static friction can be calculated between the tires and the road. Now, calculate this value and you will put in the question box right below this video as an assignment in class. So this is the process that we can use to determine the coefficient of friction between the tires of a car and the road by determining the stopping distance. And you can actually go out and do this on any road. Now, what about the stopping distance downhill? In order for us to determine the stopping distance downhill, we still have to calculate its acceleration downhill. And to do so, we have to start first by doing our free body diagram. A free body diagram is a diagram that only shows the forces exerted on the system. It does not show the forces exerted by the system. Our system in this case is the car decelerating downhill. So we have the weight acting vertically downwards. Take note, the weight always acts towards the center of the earth vertically downwards in this particular case. Now, we have the normal force acting on the car, which is perpendicular to the plane. I'm going to call that N. Just let's assume something. The friction force that acts between the car and the surface is static friction. So the tricky question is, in what direction is the static friction acting? Remember, static friction always tend to oppose the direction in which the car would move if it were just about to move. Let's say that you leave the car at rest on an inclined plane. In what direction will the car turn? Will the car have a tendency to slide? Definitely the car will have a higher tendency to slide downwards. And if the car doesn't slide downwards, it means that there is a static friction force acting upwards. So in this case, unlike in the first case, the static friction force is acting in this direction. So this is F static. Now here's the deal. We can resolve the weight into two components, but before I would do so, I'm going to orient my x-axis such that it lies along the plane and in the direction of motion. This is a very critical point that you need to always do if you want your answers to be simple. Now, this angle is theta, so we can resolve our weight into two. You'll have the component perpendicular to the surface. This is mg cosine theta, and you have this component parallel to the surface. This is mg sine theta. So the next thing that we will do is to apply Newton's second law equation for the car. Let's start with the y direction. The sum of forces along the y direction is 0. This implies that n minus mg cosine theta is equal to 0. In other words, n is equal to mg cosine theta. This gives us the normal force that the road exerts on the car. Remember, it acts on each tire, so I've bundled all of that into one big force, N. So let's sum the forces along the x direction. This should be fun. This is going to be equal to mg, the sine of theta minus f of s. And all of this is equal to ma because the acceleration is along the x direction. But this is F max. Now, by definition, F max of S is equal to mu Sn, which is equal to mu S mg cosine theta. So all we have to do at this point is to substitute the expression for the static friction back into our equation number 2. If we do that, we will have a very beautiful equation given by mg, the sine of theta, minus mu s mg, the cosine of theta, equal to ma. Now, guess what? We can factorize out the terms common. And if we do that, we are going to have mg bracket, the sine of theta minus mu s, the cosine of theta, all of this equal to ma. Notice something incredible. The masses will go away. And if the masses go away, we will be left with the expression for the acceleration to be given by g bracket, the sine of theta minus mu s, the cosine of theta. This right here, my friends, gives us the expression for the acceleration of the object down here. It is critical, if you have to survive in this class, for you to know exactly how to derive this expression. I often give this in an examination. The next step is for us to calculate the stopping distance. We know for sure that v squared is equal to v naught squared minus 2a delta x. Why minus? The minus sign is because the car is decelerating to rest, which means that the final velocity is 0. Hence, our stopping distance delta x s will be equal to v naught squared divided by 2a. This will be equal to v naught squared divided by 2g bracket, the sine of theta minus mu s, the cosine of theta. This right here, my friends, is the expression to calculate the stopping distance of the Tesla down the hill. So what you can do is theta is actually 15 degrees, mu is 0.5, g is 10, and v0 is 70 miles per hour. You can substitute the values into that formula and put your answer in the assignment box just below this video. Thank you so much for your time. I do appreciate your commitment for this course. Remain highly blessed. This is Kimal Honor speaking. Thank you. Bye-bye.